All right, so let's take a look at the Unit 6, Lesson 6 practice problems. I'm going to work in the book. If you're in my class, you have the option to work in the book or do the same like questions in the online version. If you're in Mr. Wong's class, I don't know, you got to do whatever he told you. I don't know what he told you. I'm in my classroom today at Willard, and when we're at Willard, we have to have our masks on, even if there's nobody else in the room with us at any time, which is the case for me right now, because who knows who could walk in. So got to keep that mask on. My mask always shift around in my face a lot, though, so you're going to see me doing this stuff. All right, so let's get started. It says, mentally determine the value of x that makes each equation true. So when they say makes the equation true, they're saying what number could you substitute in for the variable, and then both sides of the equation would have the same number. It would be a true equation. This is the number that you get when you solve an equation. So they're essentially saying mentally solve this equation. So the first one says some number minus 1 equals 5. That one's easy, right? That's got to be a 6. So I'm going to write x equals 6. I think they get a little harder than that. All right, the next one says 2 times some number that is x minus 1, right? Some quantity that is x minus 1 as a whole equals 10. Well, I know that 2 times 5 equals 10, right? So that means the stuff in the parentheses must equal 5. Well, the stuff in the parentheses is some number minus 1. So that means that the sum number must be 6. Oh, I haven't done these yet, but I feel like I'm seeing a little pattern. Are they all going to be 6? Let's see. Next, this one says 3 times some quantity that's in these parentheses has to equal 15. Well, I know that 3 times 5 equals 15. And the stuff in the parentheses is some number minus 1. So that some number minus 1 has to equal 5 again, which means, again, x is going to equal 6. I see what they're doing. All right, and on the last one here, it says 500 equals 100 times this quantity x minus 1 again. And I know that if it was 100 times 5, we'd have a true equation, right? 100 times 5 is 500. So x minus 5 has to equal, or x minus 1 has to equal 5. And so x is going to equal 6 again. All right. So next, it says explain how each part of the equation 9 equals 3 times the quantity x plus 2 is represented in the hanger. Okay, so, well, the hangers are just like equations. They have sides to them, right? A right side and a left side. This is your right side. This is your, no, it's not. Oh, I don't know my right from my left. Oops. This is your left side. This is your right side. Okay, so, well, let's talk about the left side first. The left, which is 9, has 9 1-pound weights. I guess they're weights. I don't know. Okay, and then on the right side, which is 3 times the quantity x plus 2, right? When I say the quantity, that's my way of verbalizing the fact that those things are in parentheses. And it kind of just acknowledges the fact that it's supposed to be one number. It's some unknown number plus the 2, but then you think of it as one number altogether. Okay, well, it has these 3 sections where each one has an x and two weights to it, right? So each one of these is an x plus 2, and there's 3 of them. Has 3 sections with an x and 2 1-pound weights. All right, let's move on. It says for question 2.1, see if we can get this in focus a little bit, maybe zoom in. Write an equation that represents this hanger. Okay, well, let's do it side by side. We've got our left side first, and our right side we'll do second. The right side's obviously going to be the easier side, right? Okay, so on the left side, I see 1, 2, 3, 4, 5 quantities that are all the same. And now it's really important to notice that they're all the same. There's a 2 and an x, 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 and a 2 and an x. If one of them was different, you can't just like count them up the way that I'm doing right now. But since they're all the same, I've got 1, 2, 3, 4, 5 of these quantities. So each one of the things that I circled in the box, I'm calling a quantity. So 5 times the quantity, well, each one of these things has an x plus a 2. So x plus 2, that's my left side. And then my right side is just an 11, right? That's the easy side. You could also do this equation by just counting the stuff up. Like instead of calling each one of these x plus 2, just look at everything you have. You got 1, 2, 3, 4, 5 x's. So we write that as 5x. And then just add the 2's up. 2, 4, 6, 8, 10. So plus 10 equals 11. Now, if you're good with your distributive property, then you know that if you were to distribute this 5, you would get 5 times x equals 5x, and 5 times 2 is 10. So these are equivalent ways of writing the equation. Just one we would call it factored form, and the other one in standard form. And so 2.2 wants us to find the value that makes the equation true. That is just another way of saying solve the equation. When you solve an equation, you're finding the value that you can put in for the x that makes the equation true. I'm going to use the orange one to solve it. No particular reason why, just because it's the lower one, I guess. And so the way I do this is I look at what operations are happening to my variable. So when I look over here, I see that x is being multiplied by 5 and it's being added to 10. I want to essentially remove these in opposite order of GEMDOS. So if I was doing GEMDOS, I would multiply first and then add. So because I'm working in reverse order, I'm going to deal with the addition first and then the multiplication. The way I deal with them is removing them through the opposite operation. Where I see addition, I'm going to use subtraction. And where I see multiplication, I'm going to use division. So I want to subtract this plus 10 away. But if I do it to one side of the equation, I must do it to the other side of the equation. This is how we keep things balanced. Okay, so plus 10 and negative 10 or minus 10, whatever you want to call it, those make a 0 when they combine. And so that's what mathematicians mean in this case when they say they cancel out. And so 5x stays. I haven't done anything to 5x. I bring my equal sign straight down, and then 11 minus 10 is 1. Now I'm going to divide both sides by 5 because my variable is being multiplied by 5, and I want to sort of undo that or reverse it. So let's see here. I can use a division. I can use a fraction bar to mean division. And so I'm just going to put a fraction bar under here showing that I'm dividing by 5. But I do it to the other side as well. And look, it kind of shows me the answer when I do this, right? The 5 on top and bottom of this fraction, they make a 1, so they're going to cancel out in this case. So I have 1x equals 1 over 5, 1/5. There's my answer. So that's the answer to 2.2. X equals 1/5. We would call that number the solution, or we can call it the number that makes the equation true. Those are the same thing, because that's what a solution is. It's a number that makes the equation true. All right. 3.1, they want us to draw a hanger that represents the equation 12.7 equals 3x plus 0.7. Okay, so I guess I'll make these little things here. And then I'm going to make one big box on this side that has like 12. And then I'm going to make a little box underneath it that has the 0.7. So there's my 12.7. I think you could have just made one big box that's 12.7. I don't know if you have to do it this way. You can make a bunch of ones that add up to 12.7, whatever. All right, let's use green on the other side. So on this side, I'm going to make 3 boxes. Oops, I don't know why I made that line so long. And each of these is going to be worth x. And notice I tried to make these 3 boxes be about the same as the 12, because I know that the last thing I have on this side is the 0.7. And well, these 0.7s, they kind of like go together, right? So the 3x's must equal the 12. And so that's going to help me sort of solve this, right? I know that 3x's have to make up the 12. You could probably figure that out in your head that this needs to be 4, 4, and 4. So we already know the answer is x equals 4. But let me show you how to write this out properly. So let's see here. 12.7 equals 3x plus 0.7. I want to get rid of this plus 0.7, so I'm going to subtract it from both sides. And that's essentially the same as like crossing both of these little boxes out here at the end, right? We're just taking the 0.7s away. And what we're left with is just 12 equals 3x, which is what we just talked about, right? We said, oh, the 3x's must be the same as the 12. That's all this equation's trying to say. And so in your head, you probably said, okay, well, let me just figure out what goes into 12 3 times. Let me divide 12 by 3. That's exactly what we're going to do. We're going to divide the 12 by the 3, but we have to do it to both sides. And what's left is 4 equals x. So there's your solution, or your number that makes the equation true in this case. All right, so let's go on to the next one. Zoom out a little bit. And it says, Haley drew this diagram to represent the equation 2x plus 16 equals 50. But she made a mistake. Explain the mistake Haley made. Okay, so what I see here is a box that has a 2 plus a box that has an x plus a box that has 16. She meant to have 2 boxes with x in them, or a box with a 2x in it, right? She didn't represent 2 times x in this diagram. She represented 2 plus x. So let's see here. She should have had 2 boxes with x because that's what 2x means. You know, I know that in my class, and I would imagine probably in Mr. Wong's class too, a lot of students on the most recent quiz showed that they didn't understand that 2x means 2 times x. A lot of students actually thought it did mean 2 plus x because they put their value for x in there and then they added. They're supposed to multiply there. So 2x means 2 times x, or that you have 2 x's. And so there should have been 2 boxes with x there. So what equation does Haley's tape diagram represent? This one that I wrote right here. I'll just bring it down this way. 2 plus x plus 16 equals 50. That's the equation that she represented with her diagram there. And so make a new diagram that correctly represents the situation. Okay, so what I'm going to do is, instead of having a 2 and an x and a 16, I'm going to have 2 x's, because that's what the term 2x means. And since when you're working in an equation, if there's x's in the same equation, those x's have to be the same number. And so you want your x boxes to be the same size in this diagram. You can't have like a little x and a big X in the same equation. So make that 1x, another x about the same size. Now it looks like all 3 pieces are going to be about the same, which is fine. It didn't have to be that way, but whatever. So x, 16, and then the 50 across the top, showing that this whole thing adds up to 50. And then use the new diagram to determine the correct value of x. I'm not going to use a diagram. I'm solving equations algebraically now. So the equation is 2x plus 16 equals 50. Okay, so I look at my variable. I notice it's being multiplied by 2 and added to 16. I want to work in reverse GEMDAS order. So normally I would multiply then add. So instead, I'm going to reverse that, and I'm going to deal with the addition, then the multiplication. And I deal with them by removing them through using the opposite operations. So where I see plus 16, I'm going to minus 16. And where I see multiply by 2, I'm going to divide by 2. Let's do it. I'm going to subtract 16 from both sides. What I'm left with is 2x equals 34. I'm going to divide both sides by 2. And what I'm left with is x equals 17. So there's my solution. Also, it worked out that these three pieces were about the same size because 17 is almost the same as 16. All right, last but not least, the explorer. The weight of the rectangle is 80 grams. Okay, got this right here. The weight of the triangle is double the weight of the circle. Determine the weight of the circle. Okay, so I'm going to do what's called representing one variable in terms of another variable, or quantity, I should say. I don't know, you'll see what I mean. So I want to know the weight of the circle, right? That's what it says here. That's my job. So, and I don't know what it is right now. So let me call that x. Each circle is x. Now I was given one really important piece of information. The weight of the triangle is double the weight of the circle. So that means if the circle is x, the triangle is 2 times whatever x is, which we write as 2x. So this is 2x, this is 2x, this is 2x, and this is 2x. Now we just add the whole thing up and make an equation out of it. How many x's do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's a total of 12 x's amount of weight on the left side here. So I'm going to write that as 12x. And then the left side just, or I mean the right side is just 80, right? So the equation here is 12x equals 80. All you got to do is solve that equation and you will know the weight of the circle. I'm not going to do that one for you. It's just one step. All you have to do is one operation and you should be able to get it. There you go.